Hello and welcome to my presentation. Today I present a standardized fluorescent staining method for fast and affordable microplastic monitoring and our results for application of this method in a long-term monitoring of microplastics in the effluent of a German wastewater treatment plant. My name is Michael Sturm and I work for Wasser 3.0, a German startup company which works on new and innovative methods for water and wastewater treatment. So, as we all know, one of the biggest difficulties in microplastics research is the microplastics detection and standardized microplastics detection, so we can compare our data, and also the detection needs to be affordable so processes can be controlled without too high costs, and this is the basis for regulations and laws because you cannot make laws for something you cannot measure. And also for example, removal processes, this is also essential because you cannot remove something which you cannot measure if you remove it. So fast and affordable and standardized detection is really essential for microplastics research. So we see a really high potential for the application of fluorescent dyes for microplastic analytics. And the idea behind this is that you take a fluorescent dye, mainly used is Nile red, and stain a sample which is containing natural particles and microplastics. And the fluorescent dye mainly stains the microplastics, while natural particles only show like a no fluorescent signal at all or only a really weak fluorescent signal, and therefore you can distinguish between natural particles which don't glow and microplastics which glow really bright. And yeah, the biggest advantage of this method is that it only needs a really short measurement time, no special laboratory equipment. The only thing you need is a fluorescent camera or fluorescent microscopy, which is widely available. The disadvantage of this method is that natural particles can interfere and cause false positives, and some polymer types are difficult to detect. Also, this method is not yet standardized. So by the standardizing process for this method, the first step we wanted to take is the laboratory environment, what laboratory requirements we have. And of course, for a microplastic-free laboratory, cleaning is essential. Before you clean, you should always test your cloths or towels which you use for cleaning if they're really lint-free. And best for this is a black light. With a black light, you can control really well if your cleaning process is working good. Also, we applied air filters to reduce the microplastic load in the air, protective clothing, lint-free. Of course, we only use glass equipment and filtered water, and we cover everything we don't need with aluminum foil. Then the next step is, of course, the sampling collection, how you take the sample in the environment. Here we have the example of the effluent of the wastewater treatment plant, where we take the sample. And what we use is a filter cartridge with 10 micrometers and a pump and PVC tubing. And with this, we can pump a high amount of water through the filter cartridge without blocking. For wastewater, 100 liters of water are enough for a representative sample, which we could take without any problem, so no clogging occurred. And after taking the sample, we transfer the sample to a glass vessel to transport it to the laboratory and store it until we measure it. So the next step is the sample which you have in the glass vessel, which you can see in the left image. And to remove the water in the sample, which you have from the cleaning process of the filter cartridge, which is about 2.5 liters of water after the cleaning process, you filter the sample again in the laboratory over a stainless steel sieve. We use stainless steel sieves because filter membranes were not suitable. The ones we tested because the microplastics got stuck in the filter membranes and then got lost in the end. We could not rinse it off. So we used 10 micrometer filter, stainless steel filters. We filter the whole sample and then we have all particles on our stainless steel filter. We can take this filter directly, put it in a beaker, add hydrogen peroxide and then start the hydrogen peroxide digestion. And this has the aim to digest the natural particles. So the natural particles are strongly reduced while it preserves the microplastics. So we have mainly microplastics left in the sample. After this, we have a next filtration step to rinse off all the digested organic material. And after this filtration, we stain the sample with a fluorescent marker, a fluorescent dye. And this fluorescent dye selectively only stains the microplastics, but not the natural particles. And like this, we can ensure that we only detect the microplastics. After the staining, we filter everything through a black filter membrane. It must be black so it shows no fluorescent signal. And then the membrane is ready for the detection. But before, I wanted to say something to the fluorescent stain which we use. We use a newly developed and improved Nile red derivative. So in a longer research project, we tested and developed 23 new Nile red derivatives for improved microplastics detection. So before we tested them, we selected some dyes due to their water solubility and chemical structure, and then tested these most promising dyes by staining different microplastics, different polymers, and different natural particles to see how strong are the fluorescent signals with microplastics, how strong are the fluorescent signal with natural particles, and how good can we separate between microplastics and natural particles to not generate the risk of false positives by natural particles while being able to detect microplastics reliable. So this is the stain we used. It's a newly developed Nile red derivative. And then after the sample preparation process, we have our sample, as we said before, on the filter membrane, the stained sample. And because fluorescent microscopes and cameras can be pretty expensive, we also worked on a guide to modify a normal camera or a normal microscope to a fluorescent microscope by applying color filters and LED flashlights with certain colors. And like this, you can modify your own microscope with a low budget to a fluorescent microscope. And this makes this method widely available because, yeah, you can transform your microscope to a fluorescent microscope with a low budget. Currently, we are working on a paper where this will be explained in detail. And here are results. We see a wastewater sample, which was processed, stained, and then images were taken. On the left, you see the normal image, and on the right, you see the fluorescent image. And you can see pretty well that on the normal image, it's almost impossible to see what is microplastics and what not from all the particles. And on the fluorescent image, you can see really well what is microplastics due to the bright fluorescent signal. And yeah, it is quite impossible to count all these microplastics by hand. So we applied particle detection or particle counting software to analyze the filters automated. Most microscope software has this particle detection also, but you can also use open source software like ImageJ to do it. And what you need to do first is define the threshold between the brightness threshold between microplastics and natural particles. So natural particles which glow much weaker are not facially detected as microplastics. And then the software automatically detects the strong glowing microplastics, and it can count it and also measure the particle size and the area and other parameters. So this is really helpful, and it is a really, really fast method to count your microplastics. And here are the results of our long-term study, which we did in Landau in a German wastewater treatment plant in the effluent to really see and validate our method and to see where are problems, does it work well, and our results show a contamination of the effluent between 150 to only 1 microplastic particles per liter. And we were really surprised because, as you can see over the time with the microplastics concentration, we have a strong temporal variation. And we were really surprised by this because we thought we would more or less have the whole time a similar level, but it's not like this. We could prove that microplastics has strong temporal variation, and it really depends on the day where you take the sample, how much microplastics you will find in the wastewater. We also averaged our results, and we found in average 45 microplastics per liter, which when you calculate it for a whole day, it's already 306 million microplastics per liter and an estimated 726 grams of microplastics. And calculated over a whole year, we then have an estimated emission of 265 kilograms of microplastics per year emitted by a wastewater treatment plant with 5,000 people, with 50,000 people, yes. And in average per person, we have 4 million microplastic particles per year and 4.8 grams of microplastics per year emitted per person. But the variations we saw before, they are all not only between the sampling days, so they are on a much shorter time scale. We took every day 2 samples, and it took approximately 15 minutes to take the sample. Here we have between the samples 15 minutes of time, and you can see that the amount of microplastics increased by a factor of 8 within 15 minutes. So these temporal variations of the microplastics contamination are also occurring in a much lower time scale, and you need to be able to detect microplastics really fast and on a small time scale to be able to measure these fluctuations and to see how much microplastics is really emitted by a wastewater treatment plant, which will be a challenge in further research projects which we are currently working on to make this detection method even faster. And what we could also see is that we had some samples, not many samples, but some samples which were extremely contaminated with microbeads. And we think that these microbeads come from industrial processes. So, for example, when this industrial process is starting or when something in this industrial process is cleaned or whatever, a lot of microbeads go to the wastewater and then go to the wastewater treatment plant and pass through the wastewater treatment plant and go to the environment. And yeah, because it was only in a few of the samples, really irregular, we think it must be a industrial process. Yes, so finally, I would like to thank you for your attention and thank all the partners of this cooperation. And now I'm open for your questions.